I'm going to start off by thanking the people that invited me here, both Professor Zalidis over there and our good friend Yanis. And I'll also say 2 apologies when I start off. First of all, I'm going to have a presentation here. I might not stick to the slides exactly, and I'll try to adapt to what goes on. And the second apology is I'm not going to talk in Greek, because the only thing that I can say in Greek is Iasus. So I don't think we'll get very far if we start off with that, l'chaim, to life that means. So honestly, it's a pleasure to be here with you today. My background is in remote sensing. I've been working for many years. I worked on the Sur-C project, which was a radar mission on the shuttle. From there, went on to a whole lot of other projects, and I'll talk a little bit about what I've been doing. The focus is on ag-tech, agro-technology, and I'll also try to talk a little bit about tech transfer. How do I move the slides over here? That's what I was lacking. I can send satellites up in space, but this is more difficult. So I want to start off with a little bit of a background, very short, because I think we've been talking about this a lot today. But if we look at the world's population and the growth in the world's population, it's very clear that we're going to be 9.6 billion by 2050, which really means a change in the amount of food we need to supply to the population. I think there was one slide, okay. This really means that we need 70% more food than we are supplying today. To do that, either we create many more farmers. Doesn't really matter at the moment if it's in the ocean or on the land or on Mars for that matter, something that I've dealt with quite a bit. But we need to create a huge increase in calorie amount that we can supply to the population by 2050. If you listen to the previous talks, that's not going to happen because the amount of farmers is going down. It's not going up. The diet is changing worldwide. And for example, there's an increase in the amount of meat production. The increase in meat production also means that we need much more hay. We need much more food for those cows. There's also an impact on the environment. So the only way to do that is to increase the yield and decrease the input. And that's where precise farming comes to play a role. When we talk about precise agriculture, we want to provide the nutrients directly to the plant. We want to increase the yield. We want to decrease the amount of work that is required to do that. In the short time that I have, I know that you just said that there's a little more time. You're saying, give a filibuster now. I'll talk a little bit about controlled farming that is controlled from space. And if we look at this farmer here in China, on the left, anything that he does on his tractor, like many tractors in the world now, is controlled by GPS, is measured at least, not controlled. They're not autonomous yet, but it's measured by GPS. There's scales on the tractor. There's a lot of information, a lot of data that is flowing in. What can we do in precise agriculture from space already now? Very easily. So we can observe, we can measure, we can respond to changes, to variations in the field. And generally speaking, remote sensing, working from a distance, can play a major role in what I just said, in precise agriculture, in increasing the yield, providing more calories, more food to a growing population on Earth. There are many questions that we might ask, but we want to ask, what are we growing? Where are we growing it? How does it change in space? And as we look around at what is done already, you'll see that computer vision plays a key role because we're taking pictures from space. I'll go into more detail in that in a moment. And we try to estimate the amount of yield. We try to detect diseases nowadays from space. I'll show an example of weed detection as we move along. And there's much more that we can do. So as I said, we monitor the yield, we have scales on the tractors nowadays. We can actually tell exactly how much fruit, how many vegetables, and so on have come from each tree. All of that goes into GIS systems. But I'll just give you an example of one of the problems that we have with that. We collect all of the data per tree, per plant, but in essence, we're analyzing. If you look at all of the agricultural models, they look at the amount of nutrients and the amount of yield. They don't look at what happens in the tree next to it. They don't look at what happens in the water distribution underneath the soil and what is feeding what, because it's a whole system. We need to look at this as a system. When we use remote sensing, we have that advantage of looking at a large area simultaneously, synoptically. There's several models that are already used. NDVI, which is the Normalized Difference Vegetation Index, uses the near-infrared and red images, pictures taken from space, tells us something about the biomass on the ground. That's been around since 1978, I think Tucker published his paper. In essence, it's not really telling us about biomass. That's what all of these scientific papers say. But if you look at the model, the red light is absorption by chlorophyll. The near-infrared is reflection from the leaves. So it's telling us something about the health of the plants and not about the biomass. So a lawn, a football lawn, will look as though it has much more biomass than a forest because it's much healthier. That's all it's telling us. So there's a problem there. We still need to update those models. We still need to improve them. Aerial photography has been around for many years. Probably we can say, well, it's been around since about 1880, but it's being used in agriculture from World War II and on. Electrical conductivity is measured nowadays, both from space and from nearby. There are a whole lot of other things that are done using satellite images. Now, this image I created, I think, 2 nights ago when I was preparing for this, or 3. You can tell when you got the presentation. I was sitting at home, and I said, okay, if I look up into space now, where I'm sitting in Beersheba, in Israel, which is basically the Eastern Mediterranean, similar to this location, how many satellites do I have above me at that very moment? And that's the satellites. That's a map of the satellites at that very moment. That's a map of the satellites that are above me. So Earth imaging is increasing dramatically, okay? And I'm going to give a few more examples as we move along. Israel included, we launched the Venus satellite to monitor agriculture, among other things. It's not to Venus, but it's to look at Earth. Recently, there are companies now that have been established. There's the EOS Data company, which has 7 satellites, all designed for precise agriculture. That's new. Planet Labs have about 150 satellites up in space already, looking down at Earth. I think they've already got a few more even since that number. So I want to show you this number, and we're going to dwell on this for a second, or these 2 numbers. At the end of 2021, there were almost 8,000 operative satellites in space, 7,941. By the end of 2022, there were 8,200. But if you looked 1 year before that, there were only 4,000. So in 2 years, we doubled the number of satellites in space. Now, where does that doubling come from? It comes from a dramatic change that has occurred, where governments used to be the only drivers of satellites. And it was started off with the space race between the former Soviet Union and the United States. The race to the moon, it doesn't matter which part or component you take of that. And for many years, it was only governments that invested in space. Recently, there's huge private investment in space. The most common example that we like to give is Elon Musk. I'm sure you've all heard of that name. So Elon Musk has a few businesses. One is the one some people here might be driving, the Tesla, the cars, the electric vehicles. The other one is SpaceX. And there are many gifts. I didn't put one on over here because I wasn't sure how we'd be sitting, but you can see the amount of launches that he's been making with the SpaceX launch vehicle, the reusable launch vehicle. Using that reusable launch vehicle, he's cut the cost down of launching satellites. So if I go back to 1970, the cost of putting 1 kilogram up in space was roughly $100,000 in 1975 actually. What's the cost nowadays of 1 kilogram to put it up in space? $1,300, $1,300. Now, $100,000 of 1975 is not $100,000 of today. So it's a huge decrease in the cost of putting anything up in space, which means that actually universities now can launch satellites. It means that almost anyone, even people sitting in this room, have the money to put 1 kilogram up in space, a 1U satellite. The other business that Elon Musk has is his ambition to go to Mars. And for that, he built the huge Starship. And recently, we had the missions to the moon. By the way, Israel had components on that mission. We had the vests that are designed to protect the astronauts. And next week, we'll release the results of that experiment. By the way, there were 2 dolls there, one with a vest, one without a vest. The one with the vest was Noga, and the one without the vest was Helga. So the German Space Agency had the one without the vest, we had the one with the vest, and we measured how much radiation we can reduce. So his ambition is to go to Mars. To do that, he built this huge spacecraft. To do that, he's also trying to make money out of this, and he's launching many satellites. And that's where another company came in. And I'm describing all of this not because I have no interest in Elon Musk, but it describes what's happening now to the economy of space and how this will influence agriculture in a moment. Starlink. He's been launching the new internet with Starlink. He already has about 4,000 satellites up. His ambition is 10,000 satellites in this decade to replace the entire internet. That's also going to impact agriculture. So there are more and more satellites that are going up in space. Some of those satellites are Earth observing. Many of them are designed to begin to look at agriculture. If I go 7 years back, 8 years back, whenever I would say to people, I'm studying how to use space for agriculture, I always got the same answer. Farmers don't have the money to pay for it. But now the price has gone down so much that they do, and there's a new economy evolving around that. And there are more and more companies that are analyzing the images to provide information to the farmers. In Israel, this is just a map of some of our satellites, and my friend sitting to my right asked me, why does Israel have a space agency? So our space agencies, actually we have two space agencies. One is the Ministry of Defense, and one is the Civilian Space Agency, which was established in 1983, many years ago. And we launched our first satellite in 1988, the OFEC 1, Earth observing. And we're launching now more and more satellites. We have communication satellites, Earth observing satellites. We have student satellites. We have high school student satellites. We're now building in 8 schools in Israel, 8 satellites that'll be launched, designed, built, launched by high school kids. My university, my lab, we built the BGU set, which was launched in 2017, lasted 6 years. So only recently it died on us. It's a CubeSat. We've gone to the moon with a private mission. All of this is happening worldwide. Space is becoming a key player in almost anything we do. So anyone who goes outside and turns his GPS on or his maps on, Google Maps, uses space. The same in agriculture. We start mapping everything we do and improving our knowledge. So I started off by talking about yield. But as a farmer, what you want to do is not create food. You don't really care about how much food you make. What you care about is how much money you make from that crop. So it's not only about the amount of yield, but it's about the timing. If I'm a farmer in Canada, I want to produce wheat before the Chinese do it there, 1 week, 2 weeks before them, so that I get the high prices. So some of the space agencies in the world are looking at their competitors to see the condition of the agriculture in another country. This is a map here of a company in China, the China Crop Watch. And I'm not going to talk too much about China, but they are watching each other over there from space, mapping the amount of yield for different areas to control the competition. But normally what you want to do is actually beat the competition. So the European Union had a program where they were monitoring the agriculture because of the subsidies, but they're also monitoring other countries to increase the profits. So using satellite data, we can not only improve our own yield, but we can also combine that with models of crop growth in order to beat the competition and do it before our neighbor does it, to get to the market 1 week earlier. I want to give you one example, and over here there was a lot of talk in the previous session about herbicides and pesticides. This is from a project of students of mine last year, or 2 years ago actually, and we said to them, you know what, in Europe, atrazine is not allowed to be used anymore. It's a herbicide which kills weeds, but it also does a lot of damage to the environment and especially to the people that fly those planes. Most of them don't survive long because of cancer. So atrazine is not allowed in Europe, in most countries in Europe. I don't know about Greece, I'm not an expert. It's not allowed in Greece, thanks. I was guessing it's all of Europe by now. In the United States, it's still allowed. But the replacement for atrazine is way too expensive for the farmer. So he says, okay, so there'll be weeds, there'll be competition between the weeds and the crop, and I'll lose some of my yield, but I'm not going to spend more money on this herbicide. So I've done a lot of work in the past on target detection from space. Obviously, nothing to do here. So I said to my friend Yaeli Dan, Professor Yaeli Dan at BGU, If I know how to detect targets, what's the problem detecting weeds? First of all, I want to tell you it's much more difficult. Weeds are much more difficult. It's difficult to understand how they grow, where they grow, what the difference between them and the crop is. But we started a project with students, and we started building algorithms for taking first drone photographs of fields, and then also satellite photos, high-resolution satellite photos, to detect weeds. And what's the objective? To actually capture those images and then use an automatic algorithm that goes straight into the tractor and opens the sprayers only over the weed. So we don't spray the entire field. So you're saving money, first of all, and you're also keeping the environment safe. So we did a lot of work on that, and we used deep learning. I'm not going to go into what deep learning is now, not in this room, I don't think. We used several models, and we actually got very good results. 97% roughly of the weeds were detected successfully, which means that we can actually now combine that with the tractors and eventually with autonomous tractors. That's part of our objective. So I know that in the title of this session, there's also another topic here, and that's tech transfer. And we were talking about that earlier in one of the breaks. As professors, and a few of us over here are professors, our objective is to get papers out. We get measured by papers, not by the amount of tech transfer. And most of what we do works very well in the lab, but scaling, changing the scale to look at huge fields requires still a lot of work. Moving that over to the industry requires a big investment. And that's where we normally fail. And if I take this example, it hasn't been licensed yet. In Israel, we have a mechanism which is the Israel Innovation Authority. It's a government authority that invests directly in the transfer of knowledge from academia to industry. And that mechanism works well. That's one of the drivers of the transfer of knowledge in Israel and some of what you've seen in the world. You know, we're called Startup Nation, and there are a lot of secret ingredients to that Startup Nation. But one key element is investing in the failure zone, which is between academic research, basic research, and industry. On this specific project, we now can do the entire project within 5 seconds for mapping an entire field and give instructions to a tractor. So in summary, there's a growth in the use of space for agribusiness. There'll be a much bigger growth, I think, with the amount of companies that are evolving around the world. Not only the US, Elon Musk is not the only one. There are other companies that are coming along at the moment. Precise agriculture will face the challenge of food supply, will be a key element in the challenge of food supply. I think that also our chemists are going to have to invest over there quite a bit. And I'll end my part over here. So thank you.